Hello learners and welcome to practice exam number 1 with a focus on chapters 19 and 20. For this exam, you will be given 20 questions and you will have 1.5 hours to complete it. Now, we all know that learning is a process. So before you even get to this practice exam, you want to make sure you have completed all lecture and homeworks. You want to make sure you have a strategy and approach to all homework problems and, of course, to the practice exam problems. You want to, of course, make sure you've practiced any homework again and redid any kind of textbook problems if you needed. And also, you want to have made sure you went back to review your lecture notes, concepts you don't get, and also review that homework. Now, the idea behind the practice exam is that you want to have all your notes already around you. That way, if you do have to grab for something, it's already there for you. My idea is to go through all the questions with you and to make sure I'm showing you some of the notes I create on the side to help me, again, approach each of these problems. The idea is always going to be practice, approach, practice, approach. So you want to study, create strategies to approach questions, and of course, use the formula sheet that is given to you. You may not think you're given a lot, but a lot of stuff on the formula sheet is very helpful for Chapter 19 material. Of course, you do not want to cheat. Remember, cheating is going to give you consequences that are not going to be great for your overall journey in your community college journey or even your future in general. So cheating is not worth your entire future. If you know you're getting to that level of desperation, please stop and contact me first. There are other options for you. All right, folks? Now let's go ahead and get into this exam. For question number 1, it says testosterone is a male hormone. Identify the functional group circle. So as you can see, it's just giving you extra information about testosterone being a male hormone. It's not something I'm going to need or going to utilize to help me identify the functional groups. All I need to do is focus on what's circled. And this portion right here is circled. Okay? Go ahead and erase that. So as you can see, this part is circled. The first thing I kind of do is write notes for myself of like, okay, they want me to identify a functional group based on this entire picture that's given. So first thing I want to do is identify and focus on the circle, which I see here. And then I'm going to rewrite and draw this entire thing. Not all of it. This entire thing here can be seen as an R group. But I definitely want to redraw this portion of the structure. So as you can see, I have oxygen, double bonded. And we have carbons here. And of course, we have a carbon here. Now this can be seen as an R group and this can be seen as an R group. As you can see, I say R group here to specify all of this here. Another one here to specify everything else. So that's how I did it. Now that I have it rewritten and redrawn, I can say, okay, let me think of functional groups that look like this structure. So this type of question is going to be something that's very important for you to have a memory of those functional groups. What do we see here? We see 2 R groups, and then we see a carbonyl group. That carbonyl group is giving us that double bond. Now we have multiple functional groups that have double bonds. We have functional groups that only have a double bond, and then we have functional groups that have a double and single bond within that functional group. As you can see here, there's only going to be a double bond. Okay, so the ones that are just only double bonds are going to be ketones and aldehydes. Okay, and so as you can see for us, when it comes, we have to then be able to understand and know what's the difference between these 2 functional groups and their structures. So of course, I'm going to just draw what I remember. I'm like ketones. I know we're going to have, of course, the carbonyl group. It's going to have 2 R groups. That's going to be our ketones. And then our aldehyde is going to have the carbonyl group. But instead of R group here, it has a hydrogen and an R group. Okay, and that is aldehyde. So I have to think of the functional group and structure what it looks like, and then of course figure out which one I'm focused on. As you can see, which one is going to be equivalent to what we already drew here, that is going to be ketones. So I have letter B as my answer. Now let's think about this question. What did I have to do? Again, focus on what's circled, redraw what's circled, and then think of those functional groups. Yes, memory is going to be important here. And there are a couple of questions where, again, it's based off of memory. For number 2, it says, which of the following names is correct? And it gives us letter A through E as answer choices. Even one of the answer choices being none of the above is correct. So in my mind, the first thing I want to do is reframe this question so that I know how to approach the problem. They want us to figure out which one of these are correct. So another way you can say it is, can these structures exist? And how can I figure out if any of these structures exist? I can do one thing. I can draw out the structure based on the actual name that's given. Once I draw up the structure, I can look at the structure and say, okay, is this structure already good enough? Or can I make the structure better? If the structure is already good enough, I already know I have the best structure and that is the correct one and my correct answer. But if I can make that structure better in any way, that means that is incorrect because something better can exist. And so what I do is I go through and I write and draw every single structure. So let's start with let's start from the bottom down. Let's start with letter D. This is 1-ethyl 2-pentene. The ene means I'm dealing with the functional group that is a double bond. Pent means I have a group that's 5 carbons. So the first thing I'm going to do is draw those 5 carbons. 1, 2, 3, 4, and then 5. Okay. Next, it says that I have a double bond on the second carbon here. So I just have to make sure I can number. I can start my numbering here or over here. It doesn't matter. I'm going to go 1, 2, 3, 4, and 5. Now, since they're saying 2-pentene, that means that the double bond is going to start on carbon number 2. So it's going to go from carbon number 2 up to carbon number 3. That's where our double bond is going to be. It also says we have a substituent. We have an ethyl group that's on carbon number 1. So here's carbon number 1. It's telling us we have an ethyl group. Ethyl means we have 2 carbons. Okay, so that means we're going to have 1, 2. So we have 2 carbon ethyl group that's going to be on carbon number 1. Now, when we're looking at the structure, the question becomes, is this the best structure that it is, or can it become better? Automatically, I know it can become better. Why? Because the longest carbon chain is not 5 carbons. We actually can start from here. 1, 2, 3, 4, 5, 6, 7 carbons, number 1. And number 2, the double bond is not on the smallest number carbon. Okay, we want the double bond to be the smallest number carbon as possible. So that means we would have to do 1, 2, 3. It would be carbon 3, and we'd have to count this way, for example. So if I want to make the structure better, I'll be 1, 2, this is carbon 3, 4, 5, 6, and 7. And that way my double bond will be on carbon 3, and I'll have my 7. So letter D, because I can make it better, we know that this is not a correct structure. Let's move on to letter C. 2-ethyl 3-pentene, another 5 carbon with a double bond. So let's get our 5 carbons up here, 1, 2, 3, 4, and 5. We know we're going to have a double bond on carbon number 3. So we just count them. I'm going to start this way this time. 1, 2, 3, 4, and 5. So going from 3 down to 4, since we're starting at carbon 3. It also tells us we have an ethyl group at carbon number 2. So let me go ahead and erase this little portion and put my ethyl group here. So carbon 1 carbon, 2 carbons. Now the question becomes, can this structure be better, or is it good as it is? Well, let's go ahead and see. As we can see automatically, the carbons can, the actual carbon chain or the group can be more than 5 carbons, once again. So we see we can actually have 1, 2, 3, 4, 5, 6 carbons here. And also, can we actually get that double bond to be smaller? Yes, we can have our numbering start this way, for example. 1, 2, 3, 4, 5, and 6, and then we'll also have another substituent here. So technically with letter C, our methyl group now is on carbon number 4, and our double bond starts at 2 instead of 3. So again, this structure could be changed, so it's definitely not correct. Let's move on to letter B. 3,3-diethyl. That means on carbon number 3, we have 2 ethyl groups. 4-butane. Before I even have to draw this, I already see one of the biggest mistakes. We have a butane, which is a hydrocarbon, and we know it's all single bond. Do we need locations of single bond? No, we do not. So the fact that there's a 4-butane automatically tells me that this entire structure is incorrect. There's no location for single bond. Well, let's go ahead and draw it anyway. 1, 2, 3, 4. 4 carbons. They're saying we have 3,3-diethyl. So I can just go ahead and name it. Go ahead and number it, 1 through 4. And then I'll put my ethyl group here, 1 ethyl group, and then another ethyl group. So as you can see, we can definitely have more than 4 carbons. 1, 2, 3, 4, 5 carbons here, for example. Okay, so because of that, we know that that can definitely not work for us. Also, we do not need a location on something that has single bonds, so letter B is out. Now we're down to letter A and E. And a lot of folks will be like, well, automatically it's letter A. But none of the above is also an answer choice. So we must go ahead and draw out letter A. 2-methyl-1-butene. But means 4 carbon, ene means a double bond. Okay, it's telling us it's on the first carbon. So I'm going to start my numbering here. You can see the double bonds on the first carbon. We have a 2-methyl group. Go ahead and add a methyl group here on carbon number 2. Renumber it. Add a methyl group here on carbon number 2. So we have 2-methyl. Can I number this any other way? 1, 2, 1, 2, 3, 4. So we do have the longest carbon chain. That's good. Our double bonds on the smallest carbon number, which is 1. So that's great. And we have a methyl group here, and it doesn't. This constituent doesn't mess up our overall structure. So letter A definitely is the correct answer here, is the name that's actually correct based on me verifying it through my drawing. And I cannot change the structure to make it better. So that's how I got my answer here. And this is my approach. Again, you can come up with your own approach, but I always recommend write little notes out for yourself so that you can figure out how would I actually approach this type of question. And then you can go back to your homework and see, oh, have I seen this in the homework? Can I get more practice? You know you have that open practice for chapter 20, so look into that as well. All right, and number 3 says, first, name the following compound. Next, draw the skeletal structure. Well, these type of questions, the issue always is that folks are not doing the one part of the question, they're only doing half of it. So you want to make sure that you are going back to double check and read all of your questions. How do I approach this question? Well, first things first, I'm going to look at the compound that's given. This is the condensed structure that's given, and I'm going to go through and check for functional groups. So I'm like, okay, CH3, CH2, oh, I see oxygen here, CH2, CH2, CH3. So automatically I'm like, I have an organic compound that has some R group, an oxygen in the middle, and then some other R group. I can constitute that in R group, I can constitute that in R group. And of course, I have my oxygen. Automatically, based off of memory, you would know that this is what functional group? An ether. Number 1, it has all single bonds. So when you think of the functional groups that have single bonds, you're thinking amines, you're thinking alcohols, and of course, you're thinking ether, okay? That's the first thing. Because we identified the group, now we have to focus on the rules of naming for that particular group. When it comes to ether, we're still going to use the prefix, root, and suffix, but we do have a little bit of a change for our root and suffix. Our root and suffix ends up being combined. So the ending of this name, no matter what, let's just say this is number 1 of me naming, the ending of this name is going to be ether, no matter what. Now, we have to consolidate our prefixes. Prefixes are going to be based on alphabetical order. So first, we're looking at our prefix here, or one of our prefixes are going to be CH3, CH2. So that is going to be a ethyl group. So we have 2 carbons there. And then we have 3 carbons here, so that's going to be a propyl group. So what we need to do with our prefixes here is put them in alphabetical order. And this is just the rules for naming ethers. So I'm going to have ethyl, propyl, ether as the name. Okay, I've answered the first part of the question. Now I have to draw the skeletal structure for these. I'm going to go off the condensed structure. I'm going to put my oxygen in the middle. After that, I know that oxygen can make 2 bonds. Okay, so I have 1 bond here, and I know that oxygen also makes that bent shape. So I can have 1 bond here and 1 bond here, and we know that's going to be our carbon. Now, these carbons are going to be based on the substituents that are here for our prefixes. So we have a propyl group, it's going to be 3 carbons, 1, 2, 3. And we have an ethyl group, 1, 2. Okay, let me write that better. I don't know why my angling on my pen is not looking great. 1, 2, and then 1, 2, 3. Boom. Now, can I put the lone pairs on oxygen? Yes, but if you do not put the lone pairs on oxygen, it's not going to be that big of a deal, okay? Do not put it in the condensed structure, and sometimes folks forget that. I will not be taking points off if you do not have the lone pairs here, but of course, if you want to give oxygen the full octet, you definitely want to make sure you have it. All right, so this is how I would approach this question. Look at the structure that's given, focus on functional groups, identify the group, focus on naming, and of course, draw the structure based on what is given. That's my first answer, my second answer. To get full points for a question like this, you need to have both of these answers. All right, on to the next. Name the following compound and circle your answer. So you already know it's all about strategy and approach. The first thing you have to do is look at this compound. All right, I see some halogens. So I'm thinking, what did I learn about functional groups and halogens? Haloalkanes, right? So I know halogens have to be chloro or bromo or fluoro, et cetera, right? I know that. And then also look at this ring structure. What do we notice about this ring structure? Well, we know that alkanes can also have cycloalkanes, or you can even have alkenes that have cycloalkenes, for example. But we also knew that we have aromatic compounds as one of our functional groups. Okay? And an aromatic compound is like good old benzene. And benzene is going to be just exactly like the ring structure that we see here with our double bond. And so when I'm thinking of aromatic compounds, and specifically benzene, I go back to my prefix, my root, and my suffix. And guess what? Our root and our suffix are combined, so the end of the name is going to be benzene. That means we have to just consolidate our prefix, which that is going to be in alphabetical order. We also have to make sure we put the location of it. And we also just want to make sure we have the smallest number for our substituents, little stuff like that, right? And so automatically when it comes to naming this, I know the end is going to be benzene based on this ring structure here. Aromatic compound, boom, boom, boom. Now I have to make sure that my substituents here, all my chlorines, are accounted for. How many chlorines do we have? 1, 2, 3. We have 3 chlorines. So when it comes to prefixes and you have more than one of the same type, you have to do, mono, di, tri, tetra, etc. And so since this is 3, that's going to be tri-fluoro. And so we have the actual prefix portion, but what else do we need with a prefix? We need location. And so now the goal is that you're going to take that tri-fluoro and you're going to create the numbers that go before it to constitute the location of each of these chlorines here. The goal is that we have the smallest numbers that we possibly can get. So let's say if we start numbering here, 1, 2, 3, 4. So we'll have a 1, 3, 4 trifluoro. The question becomes, can I get it to be smaller? Well, let's go ahead and recount. What if we started with this chlorine? 1, 2, 3, 4, 5, 6. Okay, so that's a 1, 2, 5 trifluoro. Can we get it to be even smaller? If we go this way, 1, 2, 3, 4, 5, 6. That's a 1, 2, 4 trifluoro. Now that I've been through 3 different combinations, now I'm just going to figure out which one am I going to go with. I'm going to go with the one with the lowest possible number. So all of these are 1. So we know we can get rid of, none we can do there. Let's go with our second number. We have 3 here, so we definitely don't want that one. And then we have 2 and 2. Let's go to the next one. We have a 5 here and a 4, so we definitely want that one. We definitely want to use 1, 2, 4 because that is the smallest numbers for our substituents. So we actually have a 1, 2, 1 comma, 2 comma, 4 comma, dash, trifluorobenzene. Okay, folks? Of course, you don't need this last comma. Let me go ahead and erase that. Don't need that last comma. 1 comma, 2 comma, 4 dash, trifluorobenzene is the answer. It says circle, but I keep boxing it, so this is what it is, okay? Again, you want to look at for functional groups, focus on the naming for that functional group. And I also said that some groups are going to supersede for naming. What did that mean in this question? First, benzene, the aromatic compound, superseded the halogens here. So benzene was important for our root and suffix, and that's what helped us with naming. Then the chlorines just became extra halogens that we use for prefix or substituents. Okay, so we have to look at things that are going to supersede. For example, if we had an alcohol group, that alcohol group is going to supersede like a double bond, for example. So we have to just make sure we're consolidating those little details as well. All right, so for this question, it says, which of the following compounds exhibits geometric isomerism? So isomer means same, which is iso, and then mer means part. So it means something that has the same parts, right? It's something that has the same arrangement of atoms, but they could be have a different orientation, or they could be arranged structurally different, right? So there's 2 different types. We have structural, and then we have stereoisomers. So structural is going to be like your butane versus your isobutane. It's just different arrangement of the bonded atoms. Where stereoisomers are going to be about having the same arrangement, but in different orientation. And there's 2 types, geometric and optical, okay? Optical sometimes are called enantiomers as well. Now, why am I doing this? Because as soon as I see this question, if you don't know what geometric isomerism is, you can't really get through. So the first thing I'm going to do is try to come up with a definition to help me remember what those details are, okay? So I'm just breaking down what some isomers are in the context of organic chemistry. Now, of course, if I'm thinking, oh, this is practice exam 1, we also talked about isomers for chapter 19 and transition metals, right? But I'm only focused on the chapter 20 right now, and as I get to chapter 19 material, I'll just keep on adding it as I go along, okay? So for stereoisomers, we're looking at geometric and optical, right? The question wants geometric. That means we're focused on cis-trans isomers. A cis isomers, you're going to have the same group on the same side. Trans isomers, you're going to have different groups on opposite sides. So we have our letter A substituent is going to be on the opposite side of this double bond. Letter B is on the opposite side of this double bond. As you can see, everything is in the framework of double bonds. And so when we're looking at letters A through E for our answer choices, all these compounds are double bonds. So how do I approach this type of question? Well, the first thing I do is draw a structure and set up my double bond. So here's a double bond structure, and we know that each of these carbons here have to have their octet. And so in order to get their octet, they're going to make bonds with certain atoms here. Okay? And so our goal, or the goal I do, or my approach, is to draw out all of my double bond structures for letter A, letter B, letter C, letter D, and letter E. I just go through like this. Just set up all my double bond structures because I know this is what I'm looking at. I'm looking at double bonded structures and seeing if they are cis and trans. So let me just go ahead and set them all up. There we go. And then after I draw them, I just look at each structure and fill out all the different atoms that each carbon is being attached to. All right, folks, and this is my approach for it. And then what's the most important thing? I'm giving those carbons their octets. So for letter A, we have CH2. That means that this carbon here is double bonded to two hydrogen atoms. It's single bonded to two hydrogen atoms and double bonded to this carbon here. So I have a hydrogen here and I have a hydrogen here. Let's move forward. We also have this carbon. It is single bonded to a hydrogen and also single bonded to a methyl group, CH3. Now, could I have put this a straight line and kept it a straight line? Yes, because it's a methyl group. But I want to write out CH3 this time around. Okay, folks? And so the next thing you want to do after you have it drawn out is to tell yourself, well, okay, I have it drawn out. All my carbons have their octet. Now, does it exhibit geometric isomerism or not? So let's see. Is it cis or trans? They didn't tell you what type. They just said in general, does it exhibit? So I'm like, okay, if it's cis, we're going to have the same groups on the same side. Well, we have two groups, but there's more hydrogens. So automatically, this can't be cis or trans. We have to have two different groups. Okay, so if it was another CH3 here, sure, that would have worked because we would have CH3 and then two hydrogens. But because there's three hydrogens in one methyl group, letter A definitely does not exhibit geometric isomerism. Let's go to letter B. Letter B, we have a carbon single bonded to two chlorines. So I have a chlorine here and a chlorine here. We also have this carbon that's single bonded to two bromines. Bromine here, bromine here. Well. A lot of people choose letter B as the correct answer because they're just like, oh, this is on the same side, this is on the same side. But you must make sure you're going back to review what cis and trans looks like for us. That means for cis, you're going to have same groups at the top and bottom of the double bond. Trans, going to be on the opposite sides of the double bond. Here, they're on the same side. They are not exhibiting geometric isomerism. So letter B is out as well. Let's go to letter E. Well, letter E, we have a methyl group, CH3, and then we have this carbon bonded to a hydrogen. We also have this carbon double bonded to this carbon, which has two single bonds to fluorines. Now, of course, with chlorines and fluorines, we would have all of the lone pairs, but for this kind of question, I'm not worried about lone pairs. I'm just trying to get my structures and answer if they have geometric isomerism. Okay? Now, we have two fluorines that are on the same side, but there's too many different groups. We need two groups, okay? Two of each group, and that's it, as we can see from our overall structure here. So this does not exhibit geometric isomerism. We have two fluorines, that's great, but we need another methyl group over here, and they need to be on the same side, for example. Let's go to letter D. Now we have this carbon single bonded to two iodines, so we have iodine here and iodine here. And then we have this carbon bonded to a hydrogen and also bonded to a bromine. As you can see, we have, again, three different groups. So that's not going to work for us. There is no geometric isomerism. By process of elimination, letter C is correct, right? Letter C is correct. Let's go ahead and verify why letter C is correct. So we have a CH3 group, okay? We also have a chlorine group that's bonded to this carbon. This carbon is double bonded to this carbon, which is also attached to a chlorine group and a CH3 group. Now, as you can see, we have our CH3 groups and our chlorine groups on the same side. So this will represent cis. But even if I was to rewrite this in a different way, so for example, what if I would have put the CH3 down here and the chlorine up here? And then over here, I would have said, okay, well, what if I would have put my chlorine down here and the CH3 and kept the same after that? I still will see trans isomerism. So no matter how you slice it or how you rearrange your two substituents, they're going to give you cis and trans isomerism. So letter C is correct. But again, with these questions, it's all about your approach. Every question I show you in this practice exam will have notes or an approach attached to it. I always start off with my notes. Even when I was on my exam in school, I'm like, wait a minute, let me go out and just write out whatever I can. I look over the questions, I write out any notes I can, and I think about it, and I do my best. Okay, so that is always going to be a strategy or one thing that I do to help myself, organize myself at least. All right, so for number 6, we're going back to naming the following compound and circle your answer or box it. So first you want to look and find functional groups. You want to name based on those groups, and of course some are going to supersede others. And then of course you want to make sure the smallest number of carbon is near that functional group and the substituents all have the smallest number possible. So now looking at this, I'm like, I see a triple bond, I see all these single bonds. Triple bond is the functional group. So here's our functional group. We have a triple, okay, that's not, but you know, triple bond. That's what I'm trying to say. Not triple, I don't know what that is. So we're going to have our prefix, our root, and our suffix. Now we know it's going to end with "-ine" because we have a triple bond. The root here is going to be based on us numbering, starting from that triple bond, getting the smallest number. So I actually can start here at this part of 1, 2. If I do 3 here, I can either go this way and have 4 carbons, or I can go this way and have 5 carbons, 3, 4, and 5. So my root is going to be 5 carbons, which is going to be pent. Automatically, I can write for my name, pent-tine, as the ending. Now I need to just deal with any prefixes. So as you can see, we do have a substituent here. We have a methyl group. What's the location? It's on carbon 3. So we have 3-methyl pentine as our, no, we do not. I knew something was off. I'm missing something, folks. And what I'm missing is the location of that triple bond. Now, when you're thinking about functional groups, of course, I just said, oh, okay, double bond, it doesn't matter. I always have to go back and double check or triple check my work. So you want to make sure you have a location for that triple bond. Because we're on carbon number 1, we're going to put 1-pentine as our answer. Now for the prefix, we're still good with that. 3-methyl. Since we have a letter and a number, we do have to have a dash in between it. Okay, folks? If it's 2 numbers, we saw that we put a comma in between those. So the true answer here is 3-methyl-1-pentine for number 6. All right, and we are back with number 7. Acetaminophen is a widely used and an effective pain reliever. Great. Extra information I don't need. Identify the functional group circle. So what are we going to do? Focus on what's circled. Rewrite or draw it to enhance. Put R groups on any substituents to make it easier to draw. And then think of functional groups that look the same. So of course I see what's circled here. All this is in R group. All this is in R group. So I have R, nitrogen, attached to that hydrogen here, carbonyl group, and then another R group. Well, well, well. What can we identify? We see that carbonyl group, which again has that double bond. If it was only a carbonyl group for this functional group, then we'll say, okay, we have a ketone or aldehyde. But what else do we see? We see this nitrogen and hydrogen. We see a single bond as well. So because we have double and single bonds, there are only 3 functional groups it could be: carboxylic acids, esters, or amides. Okay? And as you can see, we're either going to be carboxylic acids, we're either going to be our esters, or our amides. Now, carboxylic acids do not have nitrogen involved, neither do esters. So automatically you can say, okay, this has to be an amide. Let's talk a little bit more. Now let's continue on and do what we always said we're going to do, which is, again, redraw and make sure we're writing out anything we can. Because what other functional group has nitrogen? Amines. So amides are going to be R groups with the nitrogen, and then it has the carbonyl group with another R group. Amines are just the R group and the nitrogen. Okay? And of course, the R group has the carbon as well. But they look very different. Amines only have single bond, whereas the amides have single and double bond. So this has single and double bonds, automatically that's going to be amide. Aldehydes, we already know that's out. Alcohol, no OH group here. Carbonyl, we do see carbonyl, but that's not the only functional group. There's a single and double bond. And now we're down to amide and amine. It has to be amide. This is definitely going to be one of those memorization type of questions. So again, if you do not know the functional group, it's going to be hard to kind of pull from even this little strategy or setup. So what some folks do is they would, like on the first question that we had in this practice exam, they would just start drawing out all of the different functional groups. Okay, they'll just draw all of them out. And then what they'll do is say, okay, I'm going to draw all of them out on question number 1, and I'll just refer back to question number 1 when I get down to question number 7, which has like a similar approach, for example. Okay, folks, so it's really all about how you want to figure this out for yourself. To me, these kind of, if I'm given a practice exam, it's all about you figuring out how you're going to approach it. Because that way, if anything is switched up in any way, you always have that approach in your head and you can remix it. But if you have nothing but memorization to go off of, then if something changes, it's going to be completely blank in your head because you don't have nothing to pull from. Okay, so just keep that in mind as well. Let's move on. Okay, so for number 8, it says, give the product of the reduction. So automatically I'm like, wait a minute, give me the product. What do we know about product? We know reactants and we know product. So that means they're asking me to create or go through some type of chemical reaction. And I have to have a product for it. So they're starting me off with the reactant. They want me to go through this process. And they want me to figure out the product. They said of the reduction of the following compounds. So I'm like, okay, well. What is reduction? All right. Well, when you're thinking of reduction, you automatically might be thinking of oxidation, and that constitutes redox. Redox is coming from oxidation and reduction, the ability to gain and lose electrons. Okay, so what does that mean when it happens in organic chemistry? We know organic chemistry has to do with carbon, right? And so it's not really going to be about the gain or loss of electrons that we normally see in our previous general chemistry realm. We're actually talking about the gain and loss of bond, particularly to a carbon. So what you do is you look at the reactant that's given and you focus on the carbon atom that has an oxygen and hydrogen attached or only oxygen. So as you can see here, these carbons have all hydrogens. They don't have any oxygens. I'm not going to bother those as well. They're basically in our group and they're going to stay the same. It's this carbon here that has hydrogen attached and is double bonded to oxygen. So you want to focus on the carbon atom with oxygen and hydrogen. Well, where does the reduction oxidation come in place? Well, if this carbon atom loses a oxygen bond here, and so if it loses an oxygen bond, if you're going from carbon, double bond to oxygen to some R group, and then hydrogen, if it loses a oxygen bond here, then it's going to be R, carbon, only single bond to oxygen, still bonded to this hydrogen, and then bonded to something else, right? We see that. So in the process of this carbon atom losing an oxygen bond, okay, in order for hydrogen to have, in order for carbon to have its octet, once you lose that oxygen bond, you're going to have to replace it with a hydrogen bond so that this carbon here continues to have its octet. Why? Because before, when it was double bonded to oxygen, it still had an octet. So if I'm going to lose an oxygen bond and add a new one, I'm going to, again, bond it to that hydrogen. So in theory, anytime you lose an oxygen bond and gain a hydrogen, you're going through the process of reduction. In contrast, the same portion here was to gain an oxygen bond and lose a hydrogen bond, we'll be going through the process of oxidation. So if this is oxidation, we'll have our R group, carbon, still double bonded to this oxygen, but we'll end up losing this hydrogen bond here and gaining another oxygen bond. Now I'll tell you, anytime you see oxygen hanging out by itself, it's always going to want to get its octet. Okay, so usually we will see it have a hydrogen attached so that it will always have the octet. So during reduction, the carbon atom is going to lose the oxygen bond and gain a hydrogen bond, as we see here. And of course, to keep oxygen having its octet, it will also gain a hydrogen bond as well. And if you're going through the process of oxidation, instead of losing an oxygen bond, you're going to gain one. And so you're going to get rid of a hydrogen, replace it with the oxygen, and of course, you got to give oxygen that octet. And so in this question, when they're actually to give the product, you always focus on that carbon that's attached to the oxygen, and you go ahead and gain or lose it and replace it with what's necessary. All right, folks, they want us to focus on reduction. So here, my product is going to look like this. I'm going to have my R group, and instead of writing R group here, I can now just rewrite it exactly how I have here, CH3, CH2, my carbon, OH, hydrogen, hydrogen. That is what my product would look like. Let me go ahead and draw it up here to make it look even better. So I'm still going to have my CH3, CH2 group. Great. Still going to have my carbon here, single bond to oxygen, and there's going to be single bond to these hydrogens here. There we go. That is what our structure will look like. Now, the interesting part about the question, if you look at the answer choice, you're like, wait a minute, there is no skeletal structure here. They are given the condensed formula. So all I need to do is take this structure and write the condensed formula. It's going to be CH3, CH2. This carbon is attached to two hydrogens and that OH group. So this is that condensed formula we're going to be focused on. Okay, so let's go through the answer choices. This is CH3, CH2, which we know is the same. So I like to go through and just double check all my R group is the same throughout all my answer choices. So that's good. Now let's talk about our carbon here. We know what it should look like. There is no nitrogens, letter A is out. Automatic. Now let's look at letter E. CO, there is no 2 oxygens, letter E is out. There is no 2 oxygens, letter D is out. We're down to B and C. Now letter C is just repeating our R group, so that's automatically out. Process of elimination is going to give us letter B. That's even without me giving any, writing the condensed structure at all, just looking at the overall answer choices, right? So that's another little strategy you can use if you didn't want to redraw everything. But letter B is actually equal to the condensed structure right here. All right, folks? Now, sometimes people may say, well, why can't I just write carbon OH-H2? The reason why you can't write carbon OH-H2 is because hydrogen does not make more than 1 bond. So you want to make sure that the hydrogens are going to be directly attached to what they're actually bonded to, and then OH, because I know this makes 2 bonds, I know it's not going to bond to this hydrogen, it's bonded to this carbon. That's how we consolidate that. All right, folks? So my approach to this question is, again, write notes about what oxidation or reduction is in the realm of organic chemistry. Reduction, losing an oxygen bond, gain a hydrogen. Oxidation, gain an oxygen bond, lose a hydrogen. Then you want to focus on the carbon atom with the oxygen and hydrogens attached only. Everything else considered R group. Then you want to, again, gain or lose the bond based on redox. So for reduction, we have that looks here, and then oxidation, we have what it looks like here. If I was to go through my answer choice and say, hey, which one will be considered oxidation? Well, it would be letter D. Letter D looks like oxidation because we have that COOH, which is what we see here, COOH. All right, so that's how I would approach number 8. Okay, so for number 9, it says, name the following compound, circle your answer. So you know, we're back to it. We know we got to look and find functional groups. We know we got to name it based on those functional groups and have the smallest number of carbon near the functional groups and their substituents. That is the approach. That's the approach I've been taking this whole time, and I'm not going to change now. So I'm looking at this structure. We know it's all about a straight up hydrocarbon, straight up alkane. That is a functional group, and that's it. So what we need to do is look at we know it's going to be an alkane. Let's write that first. Prefix, root, and suffix. We know the suffix is going to be ane. Now, how many carbons do we have? Let's get to counting. So we have 1, 2, 3, 4. Can we get more than that? Let's try. 1, 2, 3, 4, 5. Can we get more than that? 1, 2, 3, 4, 5. So it looks like it's going to be 5 carbon. Okay? 5 carbon is going to be pent. Automatically for this name, we know we're going to have pentane, period. There's no location you need for pentane or anything like that. Now, if it's pentane, what do we need to do? We need to say, okay, we have our pentane, we're kind of numbering this. Now we have these 2 substituents. So we have a substituent here, and we have a substituent here. The reason why I didn't straight up name, just because I knew it was pentane, I'm like, okay, 1, 2, 3, 4. The reason why I didn't start naming is because I wanted to identify my substituents first, and then name to where I give my substituents the smallest number. So if I start here, 1, 2, 3, it's going to be 3, 4 for methyl groups. But if I start my counting here, 1, 2, 3, 4, 5, then I can have a 2, 3 dimethyl group. See what I'm saying? So that's why I always take my time first to just look at the entire structure. So I know I have my pentane. That's already numbered. I know this is going to be a methyl group, and this is also going to be a methyl group. And since there's 2 of them, that's automatically going to be dimethyl. Now for both, you have to have a location. First location is 2. The next location is 3 dash dimethyl. And that is going to be my answer. So I'm going to have 2, 3 dash dimethyl pentane. And that's it. So again, you want to make sure that you are numbering after you've consolidated your structure. When I get functional groups like the triple bond we saw, it's easy to start numbering from there because we know that's what we do. When you're seeing straight up alkane, then it can be like, okay, well, what do I start? Here, you just want to get the smallest number. So that's why I started on this side. All right, name the following compound, number 10, and circle your answer. So we're back to it. We want to look and find functional groups, name based on the groups, and give the smallest number carbon. We know the drill, right? And that's the same thing we're going to be doing the entire time. So first things first, we want to see if we can find any functional groups. I see a methyl. Wait a minute, I see a carbonyl group. So we know we have a carbonyl group here. That's great. And if we have a carbonyl group and it's only a double bond, there is no nitrogens or any extra oxygens or anything added on, then we know that we just simply have a double bond functional group. There's 2 of them. That's going to be ketones and aldehydes. Okay? Now, the cool thing about this exam itself, and this can happen on the real exam as well, is since we already talked about ketones and aldehydes in another previous question, We already have that written down. We know that a ketone is going to have 2 R groups, and an aldehyde is only going to have 1 R group, right? So there's our aldehyde and our ketone. When we're looking at our structure here, we can say, okay, here's our carbonyl group, here's 1 R group, and here is another R group. So we are dealing with a ketone, folks. And so as soon as I'm dealing with the ketone, I'm going to go ahead and get all the information I have about naming ketones. Okay? Again, because I've already talked about ketones and aldehydes in the previous question, I just would flip back to that question and be like, okay, let me see what notes I have to help myself in this situation. And it's something you can do on the real exam as well. So we got to name this. We have a ketone here. We know our suffix is going to be -one or O-N-E. And we also need to make sure we have a location of the ketone as well. And the root is going to be based on the number of carbons. And so we just have to number the carbons. Normally you say, okay, we're going to number it by our carbonyl group. We do have a carbon right before it. So we can number this 1, 2, 3, and 4. So we're going to have a bute or 4-carbon group here as well. Okay, and then our prefix, do we have any prefixes? No, there's no prefixes. These are R groups, yes, but those R groups are going to be a part of the name when it comes to our ketones and aldehyde. Okay, so it's actually going to be a part of the name here. And so I'm looking at, I'm like, it's also going to be part of our numbering our longest carbon chain. So for part of numbering our longest carbon chain, they would not be considered those substituents there, just so there's not any extra confusion. I just circled them out that way so that I can identify the functional group, not specifically to start naming them as prefixes. Okay, folks, so just for that clarity. All right, so this is butane. So, well, we know this is bute because it's 4 carbon. So it's going to be bute, butanone. Okay, and how did I say it was butane? Because it's only going to be carbon, carbon single bonds, and then we have the carbonyl group here. So really you have butane, and then with ketones, you drop the E. So you're going to keep the butane, and then you're going to add the -one on it. So butanone. And of course, we have to put the location of where the carbonyl group is going to start. So it's going to be 2-butanone, okay? And that is the answer for number 10, 2-butanone. So for this one, again, we looked and found a carbonyl group. It was only a double bond. We had to see that anything that has an only double bond functional group are ketones and aldehydes. We went ahead and wrote those out so we can identify it. We identified it as a ketone. We decided to say, okay, what's our prefix, root, and suffix for this? We know that with a ketone or any functional group, you're always going to drop that last E, and you're going to replace it with something. When it's a ketone, you're dropping that last E, and you're going to replace it with O-N-E. And so since I only saw single bonds between the carbons here, I put butane, drop the E, and then, of course, fill out O-N-E. Then I have to put the location of where that carbonyl group is really going to start. So it's really going to be 2-butanone. All right, folks, that's how I got through number 10. And for number 11, again, we're going to name the following compound. And of course, it doesn't say it, but you're going to circle or box your answer. First, we got to look and find functional group, name them, and then try to get the smallest numbers possible. And I'm looking at all this, I'm like, okay, I'm seeing single bonds everywhere. So we're thinking some kind of alkane, but wait a minute, I see OH. This is an alcohol. Okay, so alcohol is going to be R group. This whole thing can constitute an R group, OH. So I'm going to have my prefix, my root, and my suffix when it comes to alcohol. I know that the E is going to be dropped and replaced with OL when it comes to an alcohol. Okay, folks? From that alcohol is where we want to start numbering. So right here, I have a carbon right next to this alcohol. This can be carbon 1. I can go carbon 2 here, 3, 4, or I can go carbon 1, 2, 3, 4 this way. It doesn't matter which way you go. It's still going to be the same number. So I'm going to go this way. So I'm left-handed. So 1, 2, 3, 4. That means everything here is considered a substituent. What kind of substituent? Can we already name it? Yes, we can. It's 2 carbons. You know it's going to be an ethyl group. All right. So I have my OL. My root is going to be a 4-carbon chain. So that's going to be butane. As we saw there, we're dropping the E. Okay. And then we're going to replace it with OL. So the ending is going to be butanol. Now, when it comes to our alcohol group, we also have to put the location of where this functional group started. And that's going to be 1-butanol because we know that the alcohol group is on the first carbon. Next, we have our prefix. So we've got the root and the prefix. Let's go ahead and get our prefix. We know it's going to be ethyl group. What's the location? Carbon number 2. So we have 2-ethyl-1-butanol. That is the answer for number 11. Again, focus on functional groups. As you can see, we did have an alkane, but the alcohol is going to supersede. We still have to use the alkane name in some way because we're going to drop that E, but overall, we have to show that the alcohol is a part of the structure. That's when we have the OL group attached. That's how we name number 11. And this also constitutes the end of chapter 20 material. So that's all for chapter 20 is the 11 questions. That means you want to go back, you want to make sure you're understanding this material, go back and review your homework for chapter 20 material as well. Do whatever it takes for you to help yourself build a strategy of how you're going to approach these particular questions. All right, now here is number 12, which is going to be the start of chapter 19 material. That's what I'm trying to say. So this question says, write the electron configuration for iron 3+. So they want you to write the electron configuration for this particular ion of iron. Okay, now what do we know about iron? Iron is a transition metal, and as you can see, it has a charge attached to it. Now, transition metals can have variable charges. So not only do we see iron 3+, we also can see iron 2+, for example. And our goal is to get the electron configuration based on the period of this overall transition metal and any exceptions. I did not write out the details for an exception. I just wrote the details of getting electron configuration based on the period. I write everything shorthand, so you're going to take our noble gas, NS2, N-1DX, and then we're going to have for period 6, noble gas, NS2, N-2, F14, N-1DX. Okay? Now, where are we going to get our N from? Our N is going to tell us the period that we're in. Okay, and our X is going to be a number between 4 to 10 based on the periodic table. And what I mean by that is, yes, we're going to have numbers on our periodic table. Let me make sure I go ahead and scroll to mine. So this should be a number between 1 and 10 here. Okay, based on how you number the transition metals, that's what I'll write. The transition metals from 1 to 10 on your periodic table, right? So how do I approach a question like this? Well, first, I write down all the notes I can about transition metals, what I remember from electron configuration. Again, you can remember these little details here, or you can just simply use the periodic table to get you through. I always use the periodic table first because the periodic table is set up to allow you to kind of complete electron configuration, so it makes it a little bit easier. And I always make sure I do the noble gas configuration. Another thing I do is, since they're always giving us ions, I always make sure I write the electron configuration of ground state iron first, and then I write the electron configuration of what they want, which is Fe3+. Why do I do that? Because it's going to be easier for us to be able to see where we're going to be gaining or losing electrons from the original ground state electron configuration versus just going straight to taking it away from the overall ion version. So let's go ahead and do that. For iron, it's going to be in period 4 here. So we're going to have our noble gas for iron. Okay? And so the noble gas is going to be our argon. And then we are going to be in period 4. So that's going to be 4s2 here. And then 4 minus 1 is 3. So that's going to be 3d. We're in the d orbitals here. And now our X is going to be based on where that iron sits on the periodic table. So you're looking at iron is going to be 3d6. I'm just counting straight from the periodic table to get this answer. And so literally right before manganese, you're going to go from scandium all the way to manganese, which is number 5, and iron right next to it. And that's how I got 3d6. So here's the ground state electron configuration for iron. We want the electron configuration for iron 3+. So we must make sure we're losing, this iron is going to lose 3 electrons. Where do we lose 3 electrons from first? We're going to lose electrons from the s2 orbitals first, okay? So these 2 electrons right here are going to be gone first. And then we'll start losing electrons in the d orbitals. Well, these 2 are gone. We need 3. So we also have to lose 1 here. So that's going to be 5 left over. Now, all we have to do is rewrite our electron configuration for that loss. So we're going to have our argon, 3d5. And that is our answer. So my approach here is always figure out what transition metal you are focused on. I go ahead and circle it on the periodic table for myself. And then I go straight from the periodic table, or you can just go ahead and use these small little formulas to help you go ahead and get the electron configuration at the ground state level. Once you have the ground state level, then you want to focus on the ion and take away electrons from that ground state. Go ahead and rewrite it, and you have the overall answer. For number 13, it's asking how many unpaired electrons. So automatically you have to be like, wait a minute. We're thinking about transition metals. We're talking chapter 19. Where are we going to be focused on unpaired electrons? We're going to be the p orbital, the s orbitals? No, we're talking about d orbitals. We're talking about crystal field theory and the fact that d orbitals have the ability to split, okay? And when they split, they have splitting energy. And that splitting energy is going to allow electrons to be paired up in different energy levels versus us just seeing it straight out in one line that we use 2 and 101, okay? So they're asking for unpaired electrons. They're asking for unpaired electrons in the d orbital of some transition metal. How many unpaired electrons would you expect from the complex ion? Now, let me rewrite it. CO, OH6, 3 minus. And they told us to circle our answer. With this type of questions, a lot of little details you must know. So you have to write what? Note for yourself. Number one, you want to look at this complex ion and identify the transition metal. Here's a transition metal right here. So they're asking for unpaired electrons. They're asking for how many unpaired electrons are in cobalt's d orbitals within this complex ion. You also want to focus on ligand. Okay, a complex ion means you're going to have a metal, a ligand, and some sort of charge. And that's exactly what we see here. And so our ligand is going to be based on denticity and strength. What does that mean? Some ligands are bidentate, meaning they can actually bind to the actual metal in 2 ways. Most ligands are monodentate, meaning they only can bond one single bond or one way. Okay, so we have OH minus, and if you go to your formula sheet, which is given, you get a whole list of ligands. You'll see that OH minus is a monodentate ligand. That means it's only going to make one bond. So if I have 6 OH minuses, they're going to make 6 attachments to this cobalt. Okay, so cobalt is going to have its 6 attachments. All right, and so that's the first thing to know just from this. We also see that OH minus has a charge of -1. That's what we also noticed from this overall ligand. This is information, again, that's given to you. And also from the formula sheet, you also notice that OH minus is a weak ligand. Just from knowing it's a weak ligand gives you so much information. What kind of information can it tell you? If you know it's a weak ligand, you know it has high spin. A lot of times for high spin, you'll just see me say HS. You know it also is going to be able to absorb low energy or long wavelengths. We also know, if we have that ligand, that it also has the ability to have small splitting energy, okay? And if it absorbs low energy, long wavelengths, it's going to reflect high energy wavelengths, okay? Or high energy light, for example. And everything that we see here for weak ligands, we have the opposite for strong field ligands. So strong field is going to be low spin. They're going to absorb high energy and shorter wavelength and reflect low energy. They're also going to have larger crystal field splitting. So everything is kind of opposite. You also go further and talk about diamagnetism, paramagnetism, or diamagnetic, paramagnetic. You also go further and talk about just outside of just crystal field splitting. What kind of longer, does it have the longest wavelength or shortest wavelength? Does it absorb higher energy light or longer energy light? You can basically keep on adding all these little details from knowing the notes from these ligands here. Okay? Now, why is it important to know about the ligand? Because the ligand is going to dictate how the electrons are going to end up pairing up in the d orbital. If you have a weak ligand, like this OH minus, it's going to have high spin. That means whatever electrons are left in cobalt's d orbital are going to fill all the orbitals up first before they start to pair up. If this was a strong field ligand, it'll be different. They'll pair up first before they jump to a higher energy level. So we're going to be doing high spin and fill all these orbitals up first. So now we have to ask ourselves, well, how many orbitals do we have? Here is my approach. First, you want to get the oxidation state of the metal ion, get its electron configuration to figure out the number of d orbital electrons. So we have our cobalt here, and I have my complex ion. I know I want to solve for this, so I'm going to name that X. I know I'm going to add it to 6 of my OH minuses. And our OH minus is going to have a charge of -1. And we know that the overall charge of this complex is 3 minus. So I've just effectively taken this complex and created a formula so I can actually solve for cobalt's oxidation number. So I'm going to have X minus 6 is equal to 3 minus. I'm going to add 6 to both sides. So X is equal to 3 plus. That means I have cobalt, sure, but I'm focused on cobalt 3 plus when it comes to figuring out how many electrons are in this d orbital. Okay? Why did I write ground state cobalt? Because just like we did in the previous question, I'm going to figure out what the electron configuration of cobalt is by itself before I go ahead and start taking away electrons. So let's go ahead and do that. For cobalt, we're going to have argon, which is our noble gas. It's still going to be in period 4, so we're going to have 4s2, 3d7, right next to iron, so it's going to be 3d7. Okay? Now, what do we do next? We want cobalt 3+, so we're going to get rid of this s orbital electron, and then we're also going to get rid of 1 here and leaving 6. So we're going to have argon 3d6 left over. That means there are going to be 6 electrons in the d orbitals. How are these 6 electrons going to be arranged? Well, because we're dealing with a weak field ligand, they're going to be arranged in high spin. So let's get to counting. 1, 2, 3, 4, 5, 6. As you can see, I had to fill up all of our electron orbitals first before I paired them up. That is what high spin is all about. Now that they're all paired up, this is what the overall d orbital looks like for this complex ion. Now the question says, how many electrons in this d orbital are unpaired? You have 1, 2, 3, and 4. So we have 4 unpaired electrons. That is the answer for this question. This is all about approach. There's so many little details. And I write down as much as I can about these ligands because guess what? We're probably going to have to use some of the other information in some other form of the exam. So make sure you're writing down all you can. Again, I always write down notes for my approach. Because if I don't remember all the details, at least I'm like, okay, at least I knew how to start it. Or at least I know how to get from one point here or one point there. I may not know all the steps, but do I know how to do some of it? That's how I start to build up to try to get myself partial credit in any way I can. All right, number 14 says, which of the following pairs of coordination compounds or complex ions are example of linkage isomers? Well, we're back to isomers. Now remember, from chapter 20 material, we focus on certain isomers which are still structural and stereoisomers, right? But for chapter 19, we can add more information to our isomer data. So now we can say we have isomers, we have structural isomers. It's not just going to be butane to isobutane. We also can have structural isomers that are linkage and coordination isomers. Then we still are going to have our same stereoisomers, which are going to be geometric, cis or trans, and optical or enantiomers. Optical isomers mean they have to be non-superimposable mirror images and also have chiral carbons. So what we want to do, and again, start figuring out what they're looking for. They're asking for a structural isomer, specifically linkage isomers. When I'm saying which of the following pairs, anytime they're saying which of the following pairs, you're going to be doing a lot of comparing and contrasting with pairs or groups. They're saying that these pairs could have coordination compounds or complex ions. What's the difference? What's the difference between a coordination compound and a complex ion? Well, coordination compound can still look like the complex ion. It's going to have a metal and ligand for sure, but it usually has a counter ion outside of it. And it's usually neutral. It doesn't have a charge. Whereas our complex ions can have our metal and our ligand, but it's usually going to have a charge outside of it. Okay, folks? So that's the difference between the two. But as you can see, another way of saying it is complex ions are ions with a charge, and compounds are just going to be neutral. Okay, that's really the way I look at it. So that's how I'll get rid of that information. And then when I'm thinking of linkage isomers, I have to consolidate that. This is going to be memory-based here. So I'm like, you have to just know how to distinguish between these type of isomers. So I'm like, I know it's not stereo. We're not using those. We're thinking of structural. For chapter 19 or transition metals, there are more structural isomers, which are linkage isomers, meaning that you have different donor atoms on the ligand. So if you have your metal, and say your ligand was our thiocyanate here, SCN, you can have the metal attached to the sulfur, or you can have the metal attached to the nitrogen. As you can see, it's the same kind of ligand, but the donor atom to the actual metal itself is different. This one being sulfur, this one being nitrogen. And then for coordination isomers, that is when your ligand and your counter ion are going to change. So you have your ligand here, say you have some kind of NH3 here, and you have a counter ion here. When these two swap, where now you have the bromine here and the NH3 on the outside, that means you're dealing with a coordination isomer. Okay? So when they're asking us specifically for linkage isomers, we need to go through all of our answer choices and consolidate which ones are going to be based on ligands and which ones are going to be based on ligands and counter ions. So first things first, I'm going through and I'm looking for anything that looks strange or suspicious. So let's look at letter E. I see that I do have complex ions here. We do have our ligands, but they're two different ligands. They're not the same one, so that's out. If these were the same ligands and say this was oxygen attached here instead of H2O or something like that, which technically oxygen is attached. So that's not going to work here. NH3 is not going to work either. Let's move on. Letter D. I have two ligands, NH3 and H2O, and then I have a counter ion here. I have two ligands and a counter ion here. Okay, so the ligands are the same. The only difference between these are the counter ions. Nothing to see here. They're not linkage, they're not coordination, they're nothing. Let's go up to letter A. So letter A, we have our NH3, we have our bromine as well, and then we also have chlorine. Here we have NH3, and then we have chlorine and bromine. Well, we do see a ligand switch with a counter ion. So this is a structural isomer, but it's the coordination isomer, not the one we're looking for. Now we're down to B and C. So we have NH3, we have water here, we have Br2. We have NH3, we have water here, and we have Br2. The only difference in these structures is that this has 4 waters and this has 2. This has 4 NH3s and this only has 2. Okay, so, or you can say 4 ammonia. So with that being said, this is nothing to us, right? It has nothing to do with any of the actual ligands changing their linkage to the overall metal. We don't have any issues with that. We don't have to worry about it. All that's happened here is the number of waters and ammonia has changed. Now let's go to letter C. We have our ligand here, CO, and we also have NO2. So we have NO2 versus ONO. Here the nitrogen's attached to the manganese. Here the oxygen's attached to the manganese. So because it's still NO2, the same number of atoms and everything, but just a difference in the donor atom, we can successfully say that, hey, this actually is an example or a pair of linkage isomers here. And so that's how we get letter C as my answer. For this question, let's think about it. What do we have to know? We have to be able to have previous information. So yes, there are a couple of questions here. Out of the 14 that we've done, there are about 3 that you have to have straight up background information. There's memorization. There's not real work to it. I wouldn't even have to write all this work here. I could just look through and just answer the question. But I'm telling you, for my mind, I like to write notes down because, again, it helps me kind of brain dump before I even start the exam, just get all my notes out of my head. That's what helps me. But if you don't have all these notes here, so I know I tend to say, make sure you're looking for putting your work. These type of questions you won't have much notes for if you just have a memory. So don't worry about that. You really want to have notes or work for things you know you can show work for. Okay? And let me be clear on that. The goal is that you're showing work so that I can understand how your brain got to the answer. For some people, that's going to be showing every single detail. For some people, that's going to be showing a couple numbers here and there so I can put it together. And that's it. It's really up to how you do it. And I won't really be able to understand until I see how everyone works and how you learn and how you answer questions. So we'll basically see when we get there. All right, folks, so we're on number 15, which says, which of the following complex ions absorbs? So we're talking about complex ions. We know we're going to have our metal, ligand, and some kind of charge. And then it says it's going to absorb light of the longest wavelength. Well. So they're giving us a list of complex ions here in our answer choices. And they're saying, out of all these complex ions listed here, which one has the longest wavelength? With this type of question, there is an approach. And there's 3 ways we can actually approach it. First, we can approach all these complex ions by oxidation number. The higher the oxidation number, the larger crystal field splitting. And also, if you have a larger crystal field splitting, you probably are going to be dealing with having the ability to absorb light of shorter wavelengths, right? So that's something we can look at there. We also can look at period. If you're in a higher period on the periodic table, you tend to have a larger crystal field splitting. If you tend to have a larger crystal field splitting, you tend to also absorb light of a shorter wavelength. So little details like that. But of course, the biggest portion for us to be able to distinguish all these complex ions are going to be the ligand. If you have a weak field ligand, which has small crystal field splitting, high spin, and has the ability to absorb low energy light, which means long wavelengths, then of course, if you have a weak field, you know that you want to figure out, okay, well, it's going to end up being able to absorb that long wavelength, right? But this question says longest. So that means not only do I need to know the details of weak field and strong field, I also need to use the spectrochemical series that's given to me on my actual formula sheet. That little series that's going to tell me from strong to weak how weak one of these ligands are. So for example, we know the weakest ligand is I minus, the strongest ligand is CN minus, and there's a spectrum to this. So I may get some that all are weak filled, but if I want to figure out which one's the longest wavelength, it's going to be probably something that has iodine attached, right? Just from what's already given. And of course, the goal is to compare all of our answer choices and choose the one that the question wants. So let's just continue on getting more details about the ligand. Weak filled, small crystal field splitting energy, high spin, long wavelength, absorbs low energy and reflects high energy. Strong filled, large crystal field splitting, low spin, short wavelengths, absorbs high energy and reflects low energy. What does that mean? That means it's going to absorb a certain color, and then it's going to reflect to us what we can see with our eyes, a different color. And where do we get that information from? The color wheel. The good old Roy G. Biv, okay? And Roy G. Biv is telling us, okay, whatever is absorbed, a certain color is going to be reflected, for example. So if I absorb orange, then I'm going to be seeing with my own eyes blue or indigo. If I absorb blue or indigo, then I'm going to reflect orange. And that can help us when it comes to understanding what these ligands can do. Okay? So, again, let's get to comparing and contrasting. First things first, oxidation number. So I have to look at every single one of these complex ions and figure out the oxidation number for the iron. Since we've already seen this before about how to be able to get this using complex ions, let's use what we know. We're going to take these complex ions and make them little algebraic formulas. So X is going to be our iron. We're going to add this to how many chlorines? We have 6. What's the charge on chlorine? -1. This entire thing is equal to 3 minus. Now again, I can also just go to my overall formula sheet and find chlorine and OH minus and cyanide and all the different ligands and get all their charges as well and their denticity. It's all there on the formula sheet for me. Okay? So what is this going to end up being? X minus 6 is equal to 3 minus. So therefore, we're going to have Fe 3 plus here. Let's look at this one. We're going to have X plus 6 times -1 because OH minus is -1. And this is equal to 3 minus. That means we're also going to have Fe 3 plus here. This one is X minus 6 because cyanide is also -1 here. That's 3 minus. So again, we're going to have Fe 3 plus there. So far, all of them have the same oxidation number. Let's continue on. Water is not going to have any charge. So this is going to be 0 here. That means Fe is automatically going to equal 3 plus. And then here, we're going to have X minus 6 because iodine has a -1 charge. It's equal to 3 minus. So again, we have Fe 3 plus. This means that oxidation number is out. They all have the same oxidation number. So we can't compare and contrast them with that. What about period? Well, they're all iron. So we cannot compare and contrast that way. The only way we can compare and contrast these complex ions that are given is based on ligand. Okay? So we want the complex ion that's going to absorb the light of the longest wavelength. Long wavelength has to do with a weak field ligand. So whatever one has the weakest ligand is going to have the longest wavelength. Okay? That's the first thing I'm saying here. So again, you just want to flip, 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 and you want to look at what it's ever given. Chlorine is definitely a weak ligand. Okay, so this is weak. OH is going to be a weak ligand. CN is strong, so that one's automatically out. Water is neutral, that one's out. And iodine is weak. So we have 3 weak ligands. Which one's the weakest? Well, we know that OH minus is a little bit stronger. Now we're down to chlorine iodine. Here's what it looks like. We have iodine here, we have chlorine, and then we have OH minus. So if you go this way, we're getting weaker. So that means our actual weakest one is going to be the iodine ligand. And so that is going to produce the longest wavelength. And that's how I approach this question. It's always going to be, if I need to compare and contrast complex ions, find the oxidation number for everything, figure out the period, and then compare and contrast by ligand. Those 3 things. All right, and we are back with another one. Question number 16. Which ion would you expect to have the largest crystal field splitting? Now, the cool thing is, we just saw in the previous question that we already kind of wrote out all of our notes for weak field and strong field ligands. And from those information, we know that strong field ligand is going to have a larger crystal field and weak field is going to have a smaller crystal field. So when we get down to the point of comparing and contrasting with ligands, we know that we're looking for strong field ligand and whatever the strongest one is, right? So if we're looking at that, well, okay, we know that our cyanide is definitely the strongest. and the weakest was our iodine. So when we get to that part of compare and contrast, that's what we'll know. All right, so what do we need to do? Just like everything else. In order to compare and contrast any of these complex ions here, we have to start with the oxidation number for each. And then we have to figure out the period and see if we can compare and contrast there. The higher the oxidation number, the larger crystal field. The higher the period, the larger crystal field. Okay, and that's important for this question. So we're going to have our cobalt, we're going to have our NO2. I'm just going to go through and get the charge for all of these straight up from my overall ligand sheet that is given in the formula sheet. So this is going to be a -1 charge, this is a -1, this is 0, this is 0, and this is -1. So this is going to be X minus 6, because there's 6 of them, is equal to 4 minus. This is going to be X minus 6 is equal to 3 minus. This is going to be X is equal to 2 plus. This is going to be X is equal to 3 plus, because this is 0 and this is 0. And then this is going to be X minus 6 is equal to 3 minus. So automatically, this is going to mean I'm going to have cobalt 2 plus here. I'm going to add 6 to that side. Cobalt 3 plus here. Cobalt 2 plus here. Cobalt 3 plus here. And cobalt 3 plus here. Automatically, what can I get rid of? Well, because we're comparing by oxidation number, I can get rid of letter A and letter C, because they are CO2 plus, when we have 3 plus here. So what we're really trying to consolidate is letters B, D, and E. Now, what about period? They're all cobalt, they're all in the same period, so I can't use that. I'm down to the ligand here. Remember, they want the largest crystal field splitting, so they want the strongest ligand possible. Here are my ligands. Let's list them out. I have NO2 minus, I have NH3, and I have Cl minus. Now, we know Cl minus, okay, Cl minus is over here by iodine. So we know that's out. Automatically, letter E is out. Very, very weak ligand. Let's go on. We're down to NO2 minus and NH3. We're looking at the actual spectrochemical series that's given to you, or relative ligand field strengths. We see that NO2 minus is here, and then we have NH3. So NO2 minus is a little bit more strong, and so I would choose NO2 minus and choose letter B for number 16. Okay? This is how I always compare and contrast complex ions. Oxidation number first, period next, and then ligands. When it comes to ligands, write down all those little details that we've been continually talking about over and over throughout the exam. Why is it important? Write it down once, and then you just can flip back to it for any other question you need. That's why it's so useful. Okay, so question number 17 says, what type of hybridization according to valence bond theory? Stop everything you're doing and go back and say, what was hybridization in relation to our course? Okay? For us, we have 4 different hybridization or hybrid orbitals. sp for linear, sp3 for tetrahedral, dsp2 for square planar, and d2sp3 for octahedral. And this was all based on complex ions and the amount of things or ligands surrounding those metal ions. So if there's 6 ligands surrounding the metal ion, you have octahedral. If there's 4, you have square planar. You also can have 4 with tetrahedral, and you have 2 with linear. And so to distinguish between our coordination numbers of 4, the question will specifically say square planar or tetrahedral in the actual question itself to help us distinguish those 2. Okay? So when they're asking for hybridization, that's what we're getting. We're getting our orbitals, and then we can get geometry here, and then also we can get CN, which stands for coordination number. And they're talking about all the coordinate covalent bonds that are formed based on all the things that are surrounding that metal ion. Okay? So they're asking us, what type of hybridization does this cobalt exhibit in the complex ion that we have here? So we have cobalt, I'm going to rewrite it. We have H2O, and there's 4 of them. And then we have Br, and there's 2 of them. And there is a charge on the outside. The first thing you need to do is you want to be able to get the coordination number for this metal. You want to know how many things are surrounding it. Once you have that, it's all based on memorization at that point. So we want to figure out how many things are surrounding the actual metal. We need to count the ligands, the number of ligands that are actually going to be attached to the metal. Now, when we're talking about ligands, you can't just go and say, okay, 4 plus 2 is equal to 6. You have to verify the denticity. How does this ligand have the ability to actually bond? When you have it being monodentate, that means it only has 1 single bond attachment to that metal ion. And if it's bidentate, it has 2 bond attachments. So let's pretend that water is bidentate. If water is bidentate, it has to be 4 times 2. So it'll be 8 plus 2 here. But it's not bidentate. It's simply monodentate. So that means you really are going to have 4 plus bromine, which is also monodentate, and there's 2 of those. And so our coordination number for this cobalt is going to be 6. That means there are going to be 6 things surrounding that particular cobalt metal. And so you can say, okay, I have my cobalt, I have my bromines here, and then I have water surrounding it. And these are the 6 things. Now, as soon as you know this information, this is where the memorization comes in. I already counted how many things are around it. The key word here was denticity. You do not have to remember anything. It is given in the formula sheet to you. All you have to do is just find the actual ligands and then figure out if it says monodentate, which is going to be 1 bond, or bidentate. If bromine is bidentate, it'll have to be 2 times 2 here, but it's not. It's monodentate. Okay? So once I know how many there is, as you can see, there are 6. So that means I'm automatically from memory dealing with the geometry that is octahedral. Now, when it comes to hybrid orbitals that are formed from the octahedral, that's going to be D2sp3. Let's count. We have 3 p orbitals, 1 s orbital. That's 4. And then we have 2 d orbitals, all to form this one hybrid D2sp3 orbital. So 4 plus 2 is 6, which equals our coordination number here. So I will circle D2sp3 as our overall amount. And I'm really misspeaking. It's not an overall amount. It's what my hybrid orbital looks like, okay? So it's D2sp3 here. Again, the approach is going to be find the coordination number of the metal, check the ligand denticity just to make sure you're not messing up your numbers, and then from the coordination number, get the geometry, and of course, hybridization. This all has to do from memory. A lot of times with this type of question, I simply just see folks write D2sp3 and circle the answer. There's nothing more you have to do if you just already know it from memory. Okay, so number 18 says ligands A and B automatically, when you're talking about ligand, think of a complex ion. You know it's going to be metal, ligand, and some charge. And we know that ligand has its own set of rules to go with it, right? It has its own little detail. So ligands A and B both form a complex with a specific metal ion. When the metal forms a complex with ligand A, the solution we see with our own eyes, or at least that's given, is violet. So ligand A is going to give violet. And then when the metal forms a complex with ligand B, the solution is orange. So what we see, or what's given, is going to be violet and orange. Okay, folks? They're asking us which ligand is going to result in the complex with the larger crystal field energy. So we just saw the larger crystal field splitting. We know that if you have a strong field ligand, you're going to have a larger crystal field splitting, right? So they're really asking us, hey, which one of these ligands is actually a strong field ligand? And how do we verify whether or not it's a strong field ligand? Well, it is going to be based on what we actually see and what's given, or what we call reflected in color, and versus what is absorbed. Now, I have to get my notes about ligands. A weak field ligand is going to have small crystal field energy, high spin, is going to absorb low energy color, and reflect high energy color. Where do we get this from? We got this from the color wheel, Ward G. Bibb. This color wheel is given to you as well, okay? And so, if I have a weak field ligand, it's going to absorb like lower energy colors like red, orange, and yellow, for example, and it's going to reflect our high energy colors. It's also going to have longer wavelengths. But for us, we're focused on strong field ligands because we know we want the largest crystal field. They have a large crystal field splitting energy. They have low spin. They absorb high energy, meaning violet, indigo, blue, and they're going to reflect low energy. So they reflect like the orange, the yellows, and the reds. They also have shorter wavelengths. And so the goal here is that we're comparing ligands and just simply answering the question. The question says you can either be ligand B, ligand A. The ligands result in the same crystal field energy, or the complex with the larger crystal field cannot be determined. Okay, that's what we're looking at here. Now, a lot of stuff's already given. How do we actually compare this? I always go off of what is reflected. So I get my color wheel and I say, what's reflected? We have our violet that's reflected, so that's reflected here. And we also have our orange that's reflected. And using my color wheel, I'm going to go to the opposite to get the complement of what's reflected. So I have my violet here, and to get the complement of what's reflected here is going to be what is absorbed. So anything that they give me, like for this one, ligand A, they told me that what I see or what's reflected is going to be violet. Well, guess what? The opposite of that on the color wheel is yellow. And so what's actually absorbed so that I can see violet was this lower energy yellow here. Okay, folks? And we can do the same thing with ligand B. Ligand B reflected orange. Well, what's actually absorbed? It could be blue or indigo, as we can see here, because that is going to be the complementary colors to orange. Blue, indigo. Okay, so what's reflected is going to be orange, what we see for ligand B, but what's absorbed is going to be the higher energy colors. Right? And so when they're asking us, hey, which one's going to be the stronger field? The stronger field ligand is going to absorb the higher energy color. So the only one that's going to absorb the higher energy color is the one that reflects the lower energy color, and that is ligand B. So ligand B absorbs high energy and is going to reflect low energy color, which is exactly what we see from the color wheel. It reflected orange, but absorbed blue indigo. Versus ligand A would absorb yellow and reflected violet. And so when it comes to the ligand and choice of ligand, we have to go off of what's absorbed. All right, folks? And so the one that has the absorption of higher energy is going to have the larger crystal field, and that is going to be ligand B. They're definitely not going to be the same because they're different colors. And it can be determined because we can use color in the color wheel and our information that's given about the ligand to help us answer this question. So with this type of question, the reason why I like it so much, and the reason why it's easy, as we've already been through an hour and 20 minutes of this overall practice exam, is that we've already seen a lot of information about the ligands from previous questions. And so now we can just go back and flip to the other questions and be like, wait a minute, what did I write down about ligands? What did it say about color? How can I verify this, right? So all of that is how I approach this particular question. All right. This one says, what type of geometry, according to valence bond theory? So we're talking about geometry. We saw this before with hybridizations. We gave it our hybrid orbitals. We had our sp, we had our sp3, we had our DSP, we had our DSP2, right? And then we also had our D2sp3. And we said that all these hybrid orbitals have their own geometry. So D2sp3 is octahedral with the coordination number of 6. DSP2 is square planar with the coordination number of 4. sp3 is tetrahedral with the coordination number of 4 as well. And then we have sp, which is linear, with the coordination number of 2. And we always said that when it comes to tetrahedral and square planar, the geometry will be given to you so that you can distinguish between the two of these when it comes to hybrid orbitals, okay? But this question is talking about geometry. We don't care about hybrid orbitals. We only care about geometry, and that's going to be based on the coordination numbers. So you want to first get the coordination number based on ligand density again, and then you want to get the geometry and, of course, the hybridization. So I have my manganese here. It's going to be attached to water. There's 4 of them. And it's also going to be attached to 2 iodines. It has a plus charge. I have to go to my chart that's given in the formula sheet. I'm going to look at water. I know it's monodentate, so it's only going to make one single bond to the manganese. There's 4 of them, so that's 4 attachments. I look at the iodine, it's also monodentate, so again, it's only going to want to make one attachment. That means there are only going to be 2. 4 plus 2 is equal to 6. That means that this manganese has a coordination number of 6, and therefore is going to be octahedral. Again, this is a memorization type question. If you know it, you will get the question right and you will move on, right? There is no real partial credit with this one. How can you get partial credit if you get tetrahedral square pyramidal, right? All the rest of them are incorrect. And so for this one, there's not, again, much work for you to show. Some folks will just count 4 plus 2 and just look at the overall ligand sheet on their own, count the 4 plus 2, realize it's 6, and just circle D. And there's nothing wrong with that, okay? So for this question, again, because I already had in my mind valence bond theory, hybridization, geometry, coordination number from a previous question, doing this question is just extra practice. And I can always flip back to previous parts of my actual exam to help me with this question. And of course, I have my overall notes right here. All right, folks, we have made it to our last question, and of course, the last question of Chapter 19 material. We're at about 1 hour and 23 minutes. That means we're probably going to be finishing this exam right under 1.5 hours, which is what I would expect for this type of exam. But another reason why everything's going by fast is because I have notes to help me get through. Without these notes, it can become very difficult. Not only that, I'm using previous information that I've worked on already in this exam to help me with these questions. For example, number 20 says, how many unpaired electrons? Again, we've already seen a question like this. I know unpaired electrons have to do with d orbitals. Okay? And they're saying, how many unpaired electrons will there be in a high spin octahedral complex? They're already telling you it's a high spin. So if you know it's high spin, what type of ligand are you dealing with? You're dealing with a weak field ligand because it's already telling you it's high spin. That's extra information to know. You're also dealing with something that has 6 ligands attached or surrounding it because we're dealing with that octahedral here. So I want to know how many unpaired electrons will there be in a high-spin octahedral complex of iron 2. As you can see, we have that 2 in parentheses. That's giving you the actual charge, right? So we have iron. This means it's going to be iron 2 plus. And so what they really are asking is, hey, instead of me giving you the actual complex ion like we saw in the previous question, I'm just going to tell you that you have a high-spin octahedral complex, and I'm going to give you the charge on the iron itself, and you still have to answer the question. So if they gave me the charging iron, the first thing I'm going to do is get my oxidation number of the metal ion. I don't have to do that because they already did that for me. Next, I have to get my electron configuration. So I'm going to get my normal ground state iron, which you know is going to be our argon. We also know it's going to be our 4s2. We saw this before. And then we have our 3d6. Now again, they want iron 2 plus. So we have to get rid of 2 electrons. So that means we're going to be left with Ar 3d6 or argon. All right. So we have our iron 2 plus, and we know how many electrons are going to be in the d orbital, and that is 6 electrons. They're telling us it's high spin. So that means we must fill up all these orbitals first before we pair them up. So we'll go 1, 2, 3, 4, 5, and 6. So where are we? We did our electron configuration. We got our number of d orbitals. We already know the ligand's weak field because that's given. So all we have to do is fill it out, which we just did, and then we just answer the question. They're not asking about color or magnetism, if it's diamagnetic or paramagnetic or crystal field splitting energy. They're not asking about any of that. They're just saying how many are unpaired. So let's count. 1, 2, 3, and 4. That means my answer is going to be C, or 4 unpaired electrons. I like this question because it's very similar answer, right, to the one we saw in another part of the practice exam, but the approach is different. How you go about it is different. And guess what's interesting? The notes are the same, right? But we didn't have to do a couple of things here. So I was able to cross things out. But me still writing my notes down helped me approach this problem no matter what. Okay? All right, folks, so this is how I would approach the practice exam in my own head. Again, I recommend you create your own notes. Because even some people are like, okay, I'm going to go exactly like she did on the practice exam video. And I would say, that sounds nice, but you're not me. So when you get on the exam and it looks completely different or the words are arranged differently, you want to make sure that you can actually go back and understand your own notes and your own setup and how you're going to approach it. Do not rely on anyone else but your own work and your own knowledge and the own effort that you put in. And please do not rely only on memorization except for the things that are just memorable. Like, for example, you have to memorize the hybridization portions, right? You have to memorize your overall functional groups. That's things that you have to memorize. Outside of that, it's about understanding how to put these concepts together, see them being mixed together, how to figure it out, and of course, create a strategy for yourself. I expect everyone to have some kind of strategy for themselves. If you come into the exam on Thursday, or whatever day, right, the exam is, you come to, on any exam that you have, if you come in and you don't even have any strategy for each of these questions or how to approach it, especially if you're giving a practice exam, you did not do enough practice on your own time. Okay? And I want you to also know that this is our first exam, so there's a lot of trust that has to go into it. Some people have, professors have told them one thing and it's different on the exam and everything like that. So we're still building trust with one another here. You won't know how I roll until, you see the exam. I won't know how you learn until I see how you answer it. So we'll figure it out as we go along. If you have questions, you know what it is. Hit me up, email, whatever, go to tutoring. We also have office hours, right? So make sure you go to office hours as well. Whatever you need to get through. Good luck with the practice exam. I also recommend you go back and review your homework. That is really the thing that comes in clutch when you're coming back and you're going back to review. I start lecture notes first. Get all my lecture notes, especially if you only have one to 3 pages. Collect all those notes and start reviewing concepts. And then I go ahead and review all of the practice on my homework. And then I go ahead and fight for that practice exam. Try your best to get under that hour and a half and do your best either way, folks. See you soon, and let me know if you need me.